All right, so last class we kind of left off looking at hypothesis testing with a sample mean, but we only had a sample variance. So we've done confidence intervals, we've done hypothesis testing. The last kind of stuff we're going to go through leading up into the exam is really just more confidence intervals and hypothesis testing. Now, we're going to throw a small wrinkle in it, which is we're no longer looking at one population, we're going to be looking at two populations, okay? So the idea between two populations is, so we can do the exact same thing, we're going to have the exact same sort of scenarios. We'll have two populations where we know the population variances, two populations where we are looking at proportions, and then two population examples where we have sample means, but we don't know the population variance. All the same sort of rules are going to apply as they did before to each one of these different types of examples. So it's not a whole lot new here, right? It's just we're going to be thinking about not just testing for whether one population has a mean different than a certain value, but we're going to be testing for whether or not two different populations have means that aren't equal to each other, right? So that's kind of the setup. This matched pairs, we'll save that for after the second exam. So we're just going to focus on these prior to the second exam. So we've got some motivating examples. I'll just go through the types of questions that we'll be thinking about. We're not going to do all these today, but maybe I have a sample of econ majors and theater majors. I find sample means of 45 and 33,000. Can I say with 95% confidence, or what would the 95% confidence interval be for the difference between these two salaries, right? And maybe I have some known population variances. Second kind of thing, what if I had the proportion of people in 2010 versus 2011 who were in favor of the Affordable Health Care Act? What would the 99% confidence interval be for the difference between those two time periods, right? One year it was 0.51, the other year it was 0.58, okay? Other setup, I've got texters and non-texters. I think I didn't set this, the series is supposed to be kind of texters. So if I've got differences in response times for people who are not texting versus people who are, what would the true kind of 90% confidence interval be for the true difference between the mean response time when someone's driving? Think about this as kind of like time to break between texters and non-texters, right? So that's kind of the setup, and we'll revisit each one of these examples, but that's kind of where we're going, okay? So when we're comparing two population means, when we know the population variances, we can think about from that very first population. So this is the example of what's the true difference between theater and econ majors starting salaries, right? So for, say, econ majors, if they're group one, population one, there will be some true mean, there will be some true population variance. I take a sample from that group, I take a sample of whatever it was, 51 econ majors, they're gonna have, that would be my sample size for that group, and I can calculate the sample mean for that group. Well, I can do the exact same thing, but take a different sample of theater majors, right? There will be some true population mean and variance for theater majors starting salaries, but the only thing I see is what I see from my sample. Now, however many theater majors I sampled, that will be my second sample size, right? Or sample size from my second group. I can then calculate a sample mean from that group. What's going to end up being true, and I'll return to this here in just a second, and you can kind of think about, I can try to give you kind of a nice visual of this. So let's say we were looking at starting salaries, okay? If we were able to observe what the true population means were, let's say this is like econ major starting salaries. No. How am I going to disrespect them? I don't like that, right? Here's the theater major starting salaries. And then here's econ major starting salaries, right? So the true means are right here. So if I'm looking at the difference between those means, what's the most likely value I would see if I took one sample? When we think about, remember this y-axis is kind of representing like probabilities or likelihoods. The true population mean will be the most likely value I see if I take a sample mean of theater majors, and the true population mean for econ majors will be the most likely value I see if I take a sample of econ majors. So if I'm looking for the difference in those two, if these are the most likely values that I'll see, when I'm thinking about the difference between those two, whatever the difference is between econ and theater starting salaries, that'll be the most likely outcome for me to see. So if I'm thinking about down here, econ minus the theater majors, right? If I'm thinking about the most likely outcomes I will see for those sample means, the first one would be whatever the difference is between those true population means. So the most likely outcome will be whatever that difference would be in the true population means. What are the next most likely outcomes? Well, like here and here, here and here. Now, if I'm thinking about those differences, they're a little bit less likely than seeing that difference between the two true population means. You can kind of imagine once I start getting out here, right, that large of a difference becomes not very likely for me to see. This small of a difference becomes not very likely for me to see. So because they're coming from two normal distributions, that distribution of my sample means will be centered around whatever the true difference is between these two groups. Between these two groups' true population means. Right? So if I'm looking at the difference between two groups' sample means, I know that distribution will be normal because I know the distributions of each group's sample mean will be normally distributed. Right? So that's kind of where that's coming from. And you can prove this, you can walk through the mathematical proof of this, but I think this is just kind of gives a pretty good visual. So it's going to end up being true, and this would probably have to actually, this isn't quite as intuitive, but you probably can think about what's the standard deviation going to be for the difference in those sample means? Well, it's just going to be what's the variance for each sample mean, add those two variances together, take the square root to get the standard deviation, right? Or you can kind of think about this as what's the variance for theater majors kind of sample means. So here we go. Sample mean of theater majors would be just the true variance divided by the sample I take of theater majors. What would the kind of variance be here? For econ majors, sample means, nope, not square root because we're looking at the variance. All right, so how would I get the variance of the difference between those two? I simply add those up. That would give me the variance. If I wanted the standard deviation, I would just take the square root. Right? So it may not be, we're not walking through the mathematical proof, but it kind of makes sense, right? I take the variance that I would see for each group's sample means, add those variances up. That's my new variance for the difference between those sample means. And if I want the standard deviation, I take the square root. Right? So we know now that the difference in these two groups' sample means will be the true population mean difference, and then the variance of each sample mean, or the variance for each group's sample mean added together, and then for the standard deviation, take the square root, okay? Well, this is nice because now we have a distribution that we know is normally distributed. We now know what the true mean should be, and we know what the variance should be. So you almost think about before we were looking at kind of the true mean and the variance of like one sample mean. Well, now we're just looking at the difference. So you can almost think about it as this is a new statistic that we're interested in. Not just the mean, we're interested in the difference in means. So how can we do confidence intervals? Right? Well, remember, and actually, I don't like this. I don't know why I didn't do this before. I probably didn't notice that it was running off the edge of the screen. There we go. Well, no, that doesn't look good. Hold on. A little bit smaller. There we go. All right. So if I want to build a confidence interval for what the true difference is in population means for two groups, I can't observe those true population means. All I can observe is what I see from my sample. Except for, well, that's maybe why I didn't move them. I'm going to move these around. Jeez, that's what happens when you change things and don't think about it. Okay, so now my confidence interval won't be based around, right? Before we were building our confidence interval around whatever sample mean we saw. Well, now we're just going to build it around the difference in the sample means, right? So it's very similar. Because we know the population variances, we can still use that standard normal distribution, find the z-value that's going to give us alpha over 2 on either side of that confidence interval. And then now, instead of using the standard deviation of our sample means, we need to use the standard deviation of the difference. Oops, come on. The standard deviation of the difference in our sample means, right? So we plug that into our confidence interval equation. So all we really did there was before, when we were calculating a confidence interval where we had a known population variance for one sample, we went like this, where we could plug the equation in there. Now all we're doing is take the difference, because that's the new statistic we're interested in. You can still use that standard normal distribution. And now I multiply by the standard deviation of whatever statistic I'm interested in. Well, now the statistic I'm interested in is the difference in the means. And we knew the equation for this will be equal to this. Okay? Where 1 and 2 just kind of indicate, group 1, group 2, whatever the two populations you're looking at. So it's the exact same format. It's just now we're interested in a different statistic. Okay? So if we have that, none of the steps change. At this point, it's just we have a new formula to plug some numbers into. Looking up that z-score, same exact way we did it before. We're just gonna have a few more things we have to kind of keep track of now, right? So now, if we compare these to the old steps, these are the exact same steps. We now have twice as many things to keep track of though, right? Because we have two populations. And our confidence interval equation is a little bit different, right? It still follows the same format of a confidence interval equation, but now because we're looking at interested in a different statistic, which is not just one sample mean, but the difference in sample means, it becomes a little bit more complicated, right? But really, it's not, we're not doing anything crazy new here. So let's say we go back to that example. We think about our econ majors and our theater majors. We've got our sample mean of 45,000 for group 1, or the econ group. The known population variance is 9,000. The sample size for group 1 is 40. Group 2 is the theater majors. We got a sample size of 50, a sample mean for that group of 33,000, and a known population variance of 6,000. If I wanted to build the 95% confidence interval for the difference between econ and theater starting salaries, what should it be? Well, the first thing I think is always probably the best way to do it, if we think about our confidence interval equations here, let's just figure out what the difference is that we're building our confidence interval around. So if we look here, 45,000, 33,000. So if we think about plugging those values in, 45,000 minus 33,000, right? Or our confidence interval is going to be based around 8,000, right? And then we're going to add and subtract some stuff to it, but at least we kind of know we're basing it around whatever the differences we saw in those sample means. Okay? So once I think about that, there we go. Right, next step is what's the z-value? Well, I have it here, but how did I find that? Well, at the 95% confidence interval, my alpha is 0.05. I want half of that on each side of my confidence interval, so I'll divide 0.05, my alpha of 0.05 by 2, 0.025, right? I'll go to my standard normal tables. The area I want in my tail is 0.025. It's exactly right here, so negative 1.96. Remember we said with confidence intervals, because that's already built into my lower and upper bound equation, when I look up alpha over 2, that's giving me that negative 1.96, and then to find the upper bound, I'd be using positive 1.96. Okay? So that z-value that I want to use is 1.96, right? Negative 1.96 to get the lower bound, positive 1.96 to get the upper bound. From there, it's just a matter of plugging everything in. It's not, there's no new step here. There's, looking up the z-value once I have that, just plugging in a few more values than we were before. Any questions on that before I keep going? No? All right. So if we plug everything in here, we get, and I said it was 8,000. What did I, no, I obviously can't do math. Why did no one say something to me? Right, this should be based around 12,000, right? 45 minus 33,000 is 12,000. I don't know what I was thinking. So we have this confidence interval, right? Now, it's pretty small because we had pretty low variances here, which is fine. It's just the way that the data was. But the interesting thing here is I could, with 95% confidence, say the true difference in starting salaries between econ theater majors is between, what, 11,960 and about 12,040. So I was able to get a pretty narrow range of values, okay? Now, I'm guessing the real population variances are probably quite a bit higher here, but I wanted to get, have some numbers that are a little bit easier to work with, okay? Any questions on that? Okay. Let's go work through another example. So let's say I wanted to build a 95% confidence interval for the true difference between Indiana and Ohio robbery rates. So I've got 24 years from both of these states. So my sample size here just happens to be the same for both groups. So my N1 and N2 will be 24 here. So I've got the average robbery rate in Indiana is 109. I've got a population variance of 175. Ohio, I find a sample robbery rate of 163. And then I have a population variance of 497. Okay. So from here, this is where, be careful when we look at what confidence interval we're being asked for. It's the difference between Indiana and Ohio. So right away, if I look at this, Indiana's is 109, Ohio's is 163. So what? Negative 54 there will be kind of that when I'm basing my confidence interval around, or the difference between Indiana and Ohio, right, is going to be negative, right? Now, if I'd flip these, I'll end up finding the exact same lower and upper bound, but instead of being negative, it would be positive, right? Because I didn't take the difference correctly, right? If I put Ohio first, I'm going to end up with what looks like the wrong confidence interval, right? I think if I actually do that, I probably end up with this answer, right? But it's not built around positive 54 because I was actually asked for the difference between Indiana and Ohio. So I need to make sure I'm plugging in Indiana's rate and subtracting Ohio's rate from that, okay? But really from there, I mean, we've identified the sample sizes. We have the population variances. In fact, what's my Z value going to be in this example? If we're paying attention to the last example, the Z score I need to use should just be 1.96, right? Because I'm looking at the same confidence level. Alpha's still going to be 0.05. I'm building a confidence interval. I still want half of alpha on each side, so 0.05 divided by 2. If I go to look up 0.025 in that Z table again, I'm going to find the exact same value, right? Nothing's changed there. So we identified everything we needed. The Z score, since we already had it from the previous problem, that was pretty easy to identify. From here, it's a matter of plugging things in, right? So plug them into plug our values into our equation. This shouldn't be too bad to get entered into your calculator. Now, the one thing I will say, I've seen people make mistakes using a calculator. If you try to put this all in and you're not using parentheses, if I say take the difference, hit enter, and then minus the Z score times the square root, and I've seen people, if you hit enter, you can sometimes make some mistakes. Sometimes it's easier, just like in the previous examples, maybe calculate this first, right? This standard deviation of the differences, and then plug that value in. So like create an intermediate step there. That's okay if you want to do it that way. For example, take the square root of 175 over 24 plus 497 over 24. Whatever that number is, then just write that in and plug it in. Might be a little bit easier sometimes to do that intermediate step, okay? In fact, this is always, if you like had a really basic calculator, I always tell people in these confidence intervals, work backwards, because if I put into my calculator 497 divided by 24, hit enter, and then plus 175 over 24, hit enter, then take the square root, then multiply by 1.96, then add whatever that difference is, your order of operations doesn't kind of screw you up, right? But You could do it all in one line, you know, using your parentheses correctly in your calculator, but just some hints, I guess. Okay. So why is this interesting, right? Well, this confidence interval is telling me that with 95% confidence, I can say that Indiana has lower robbery rates, right? Because the only possible values in this range are negative, right? So with 95% confidence, I can say that the mean robbery rates are lower in Indiana. Now, what if I instead, and these numbers won't line up, but I'm giving you this as an example. What if instead it was something like this? I'd found the difference, I'd built my confidence interval. Now, with 95% confidence, let's say we built this interval, I can't say anything, right? Because the true difference could be that Indiana has lower robbery rates, but it also could be that it has greater robbery rates if that difference was positive. In fact, one of the true values in this range could be that the robbery rates are no different, right? Or that difference is equal to 0. So anytime you're looking at these confidence intervals for two populations, we can really only make interesting statements or conclusions if all the values are negative or all the values are positive. If it ever crosses over that 0 threshold, one of the true values could be 0 or that there is no difference between the two groups, right? So when we're thinking about the interpretation of these confidence intervals for two populations, I'm not saying we should be trying to find, you know, the data is what it is, but it's a lot more useful. We can make a lot more useful comments if it doesn't cross over that kind of 0 threshold. Yeah.
So do those numbers, like for the example, is that somewhere in that range is the difference in the number of crimes?
Yep. So what this is saying, with 95% confidence, the true difference between the population mean for Indiana crime and Ohio crime, the true difference is, with 95% confidence, somewhere in this range. So if it's somewhere in this range, the only values in this range are negative values, right? The problem becomes, we have an example like this, well now the true difference could be 0.
I guess what I'm asking is, like, do those numbers represent like the number of crimes, like the difference in the quantity of crimes committed, or is it just like the range?
It's the difference in the quantity of crimes between Indiana and Ohio. Yeah. But those, you know, it's not one specific value. It's a range of values that could take on. Yes. Yep. Somewhere in that range is the true difference between the crime rates of the two states. Yep. Any other questions on that before we keep moving? All right. So if we can do confidence intervals for these types of problems, we can also do hypothesis testing. Right? So hypothesis testing is a little bit different here. What we're going to do is call the difference between the two means capital D. So if I think about x1 minus x2, that's kind of like my sample. So like D hat, I guess. The true population difference between the means would be capital D. We're going to have some assumed true value for what that difference is. Call that D subscript 0. Okay. So every example we're going to use, we're just going to set this equal to 0, right? Because what that's really saying is the true difference greater than 0, less than 0, or anything other than 0? What we're really saying is, does one group have a higher mean? Does one group have a lower mean? Or do they just have different means? Okay. So we can think about the 3 types of tests we have, and now it kind of becomes easier because the assumed true value, before we usually had to identify that, it's always going to be 0 now, right? So we're going to have a right-tailed, left-tailed, and a two-tailed test still, right? Same sort of convention as we did before, and how we identify that. We identify it off of the alternative hypothesis. And we can start to conduct hypothesis tests, which the steps look exactly the same. No matter if we do the p-value or critical value approach, the only difference is our test statistic, right? It's going to look a little bit different than it did before. Okay? So let's think about 2 of those things that I just said. The first being some of our hypothesis tests, right? So if I'm thinking about the true difference between my population means is represented by kind of capital D. Right? So what we're going to say is, if I wanted to know for example, let's say I had a hypothesis test where the null was, is that true difference greater than or equal to 0? Or my alternative would be that it's less than 0, right? So if I'm saying, is that true difference less than 0, what I'm really saying is that, right? All this capital D represents is the difference in my population means, right? So if the difference in these two groups' population means is less than 0, what I'm also saying is just that, is group 1's mean less than group 2's mean, right? Because that's the only way I'll get a difference that's negative, right? So even though we're writing the null alternative, kind of using this capital D, what we're really saying is that for a left tail test, it's saying, is group 1's mean less than groups 2? If we had a right tail test, all we're saying is groups 2's mean greater than, is group 1's mean greater than group 2? And if we had a not equal to test, all we're really saying is, are these means different from each other? Okay? So that's why, these hypothesis tests make a lot of sense if we set that assumed true difference to 0. If I don't set that assumed true difference to 0, so let's go back to where we were doing a left tail test. Let's say I want to know, is that difference less than 20? I knew that marker was starting to die. Well, now, this is that less than 20? Or I can think about it as like this. So now what I'm really saying is the difference between those means, not just as group 1's less than group 2, but is group 1 I guess you could say it differently. Is group 2 at least 20 higher than the mean of group 1, right? Now, I'm not going to deal with any of those. We're always going to use 0. You can kind of see why, because when we're using 0, we're often interested in, is group 1's mean higher, is it lower, or is it just anything different, right? What you could start to do tests for, is it 20, whatever the units, 20 crimes higher in Indiana versus Ohio or something like that, okay? The second thing that I mentioned that I wanted to kind of go over is first of all, are there any questions on this before I keep going? Okay with that. If I'm calculating my test statistic, before, what we had was take your sample mean, subtract the assumed true mean, divide by the standard deviation of that, which was the square root of the sample or population variance over the sample size. Now, if I want to calculate a test statistic, right? Remember, the format's always the same. I take the statistic I'm interested in. So now I'm interested in the difference of those two sample means. Subtract the assumed true population mean of that, or population value of that statistic. Well, now the way that we were denoting this was our assumed true difference. But I told you, for all the examples we're going to look at, we're always going to use 0. So you can essentially ignore this for the sake of what we're doing in this class. We'll then divide by the standard deviation of the statistic we're interested in, which is the standard deviation of the difference in our sample means. But we know that the equation for this is the square root of each group's population variance divided by that group's sample size. So it's still following the same exact format. We're still calculating a z value. It's a z statistic, a test statistic. But how do you do that? You subtract the assumed true value of that, or the kind of assumed true mean, and divide by the standard deviation. It's just that we're looking at a different statistic now. Okay? And making this 0 kind of makes this test statistic equation a little bit easier. I believe that should be, well, I'll come back to this in a second. Right here, right? And you can almost think about whatever the difference in the sample means you find. If you really want to, you can also think about this as kind of like d hat, right? The sample difference you found. Okay. So here's our test statistic equation. If we go back and think about critical values and p-values, nothing's changed. We find p-values and critical values the exact same way. Once we turn our sample evidence into a test statistic, to find the p-value, you would still look up the area that's like more extreme than the test statistic. It's a two-tailed test. We still had to do that kind of multiply by 2 to get the total p-value. We're looking up critical values. It's still whatever value would give me alpha in my tail, or if it's a two-tailed test, alpha over 2 in each tail. It's the exact same procedure as we followed before. The only step that changes with hypothesis testing for two populations, I guess you could say the null and alternative hypothesis, identifying them changes a little bit, right? But the only other thing that would change is you have a slightly different test statistic equation. All the other steps are identical. Find the critical values the same way, p-values. You still reject if the p-value is less than alpha. None of that has changed, okay? So let's think about an example. So let's say I've got kind of an older time period and a newer time period. So 1990 to 2011, I've got 22 years. The average number of tropical storms in the Atlantic was 15.5. And I know from historical data, kind of the population variance there is 25.5. I then look at an older time period, 32 years, find the average number of storms is 9.7, and I have a population variance for that time frame somehow as well. Now, just like the one population examples, we start out here. In most contexts, this doesn't make sense. We're not going to have the actual population variance. We probably only have a sample variance. But this goes, it's the same idea as one population. Maybe we somehow know like the variance on the production of a process of a machine or something like that. So we'll walk through an example so we get familiar with this, and then probably, you know, push it one more step, which is what if we only have sample variances eventually. So if I want to know whether tropical storms have increased in recent years, right? So really what I'm saying there is if they've increased in recent years, and we'll just kind of use the end date for both these time periods, what I'm really saying is that mean of 2011, or the time period that ended in 2011, greater than the mean, I think it was 1989. I don't remember the exact one. I'll have to look back in a second. But what I was really saying is the new time periods mean greater than the old time periods. If I want to rearrange this to look like a difference, I subtract the mean of the older time period from both sides. What I'm really testing for is that difference a positive value? Because if they've increased in recent years, when I take the recent year average, subtract the older year average, if it's went up, that'll be a positive value. So if that's what I want to test for, what would I assume is true? I assume the opposite of that, and that's my null. So I'll assume that the difference is less than or equal to 0, right? So less than or equal to 0 is what I assumed was true, because what I wanted to find is that difference greater than 0. Now here, these other examples shouldn't make any sense because I told you already that the assumed true difference I'm always going to use in these problems is 0, okay? So what type of tailed test do we have here? If this is our null and alternative hypothesis, we look at the alternative hypothesis. What type of tailed test do we have? Yeah, greater than or right tailed test. So the next step we could do is, well, what if we wanted to use the critical value approach? Okay? What would the critical value be if we wanted to do this hypothesis at the 5% significance level? Okay? So what we're doing there, remember, we know the population variances, so we're back to being able to use the standard normal distribution. I have a right-tailed test, so I want the critical value. That gives me alpha of 0.05 in that right tail, okay? So how can I find that? Well, I've got my standard normal tables. If I look up 0.05, why won't that be the value I want? If I go to the table, look up the area I want in the tail of 0.05, I'm actually going to find this value, but negative, right? Because remember, the table is the area in the lower left tail. So I could do that. I could look up 0.05 and just remember, it's a right tail test. It's that value, but positive. Or I could look up the area to the left, which would be 0.95. Okay? Any questions on that?
Not about that, but why
Yeah.
do you assume the true difference is 0?
Why do we assume the true difference is 0?
Yeah.
Or like greater than or less than 0? So we don't have to. We could do it for different values, but the reasoning behind this one, like for example, the alternative hypothesis, when we said, if I want to test for whether or not group 1's mean is greater than group 2's, what I'm really saying there is the difference between the two greater than 0? Like I just rearrange that. So the reason why I'll use 0 for all the examples and why quite often you do just use 0. In fact, some of the stuff we'll look at in Excel, the built-in assumption, you can't change from 0. Because more often than not, you are trying to test, is group 1 have a higher mean than group 2? Does it have a lower mean than group 2? Is it anything different than group 2? Very seldom would you have an example where you want to say, is it 50 points higher than group 2? Well, you could do that. But more often, I would say the majority of what you would be using hypothesis testing for between two populations is just to see, is one group's mean higher, is it lower, or is it are they just different? But you could get real crazy. You could say like, is group 1's mean 50 times greater than, right? Group 2, in which case you can kind of think about, there it gets kind of tricky because now you're trying to think about the difference, and I've got this times 50. Well, how do I write the difference? So it gets a little bit, you can add things to this, but for the sake of what we're going to do, we're just going to use that as 0 because those are the most common types of hypothesis tests we want to do. Does that answer your question? Any other questions there? All right, so we'll go to the tables. We can look up the area of 0.05. It's in between these two values. So negative 1.64, negative 1.65. So we use negative 1.65, the kind of higher and absolute value of the two. Remember, it's a right-tailed test, so the value we actually want is 1.65. Okay. So we've got this critical value of 1.65. Kind of draw an arrow into the tail, or think about it as anything kind of more extreme than that critical value is my rejection region. Okay. From there, this part is if we know the test statistic equation and we have all the information that we need, finding the test statistic, it's really nothing I can show you in terms of like making it make more sense. You have an equation, you have the values for the different parts of the equation. It's just a matter of plugging and chugging, right? This step is just a matter of once I've identified I have two sample means, I'm looking for the difference in those. I've got my two population means, my two sample sizes. It's a matter of just plugging everything in and kind of making sure I don't make a mistake with my calculator, basically. Okay? So if I find this test statistic of 4.9, hopefully we're getting kind of comfortable seeing these values. For a typical kind of hypothesis test, if I see something 4.9 standard deviations away from the assumed true mean, that's pretty far. In fact, if I try to find the p-value for this, which we'll do in just a second, it's not even on my standard normal table. So we have the test statistic, though, just to kind of complete out that critical value approach. Here's my rejection region. Here's my critical value. My test statistic was 4.9. I'm clearly going to be in that rejection region, right? Very clearly in that rejection region. Now, if I wanted to instead have found the p-value, I don't even really have this drawn very well to scale, but you can imagine what I want to do there. Once I've turned this into a test statistic and I see 4.9, my p-value would be, for a right-tailed test, the area to the right of it. Okay. Well, if I use the table, I can look up 4.9, it'll tell me the area to the left, and then I'd have to subtract it from 1, right? Well, the problem is if I go to that standard normal table, what am I going to find? The area to the left of 4.9 is approximately what? Close. The area to the left of 4.9 is going to be approximately 1, right? The area to the right of it will be pretty close to 0. So if we go down here, notice a test statistic of 3.99, the area to the left is almost 1. So if I'm thinking about the area to the left of 4.9, even closer to 1, right? So there's going to, the area to the left would be really close to 1, which means 1 minus 1. The area to the right is going to be really close to 0. Okay? Any questions on that? So similar, like we rejected using the critical value approach. If I find a p-value of approximately 0, well, I only reject if it's less than alpha. Doesn't matter what alpha I choose. If my p-value is pretty much 0, I could probably reject this one at the, we could even do the 99.9%. Right? We could choose like a really small alpha. So we could probably reject this at any level we want to, right? Because the p-value is pretty much 0. Okay. All right. Let's see. Where did we leave here? Any questions on that before I keep moving here? Okay, so next class, we'll start doing proportion examples. Same type of idea. Things change a little bit more with this one, but same idea. All of our steps are really the same. We're just going to have slightly different equations for our confidence intervals and for our test statistics. But I want to go through something that hopefully just for hypothesis testing makes it make a little bit more sense in general. Okay. So a long time ago, and we just haven't gotten around to it because of I just want to make sure I got through other things first. I had this, what was it called? Hypothesis testing, or HT example tuition, right? So what we were saying way back a long time ago, and we probably have gotten a little lost in the weeds of the actual formulas we're using and things like that. But the original thing with hypothesis testing, we started out saying, well, look, if I assume some value is the population mean, let's say that in fact it ends up being exactly what the population mean is. Like after the fact, we can kind of see, okay, our assumption was right. Well, we said if this in fact ends up being the true mean, when we see sample evidence that's this far away from that assumed true mean, and we set alpha to say, well, look, the probability of seeing something out this far away from the assumed true mean, even if it was, in fact, the true population mean, the probability is so low here, we're okay rejecting it. And we know that if this ends up being the true population mean, we'll have made errors alpha amount of the time or alpha times 100% of the time. Right? So anytime we see a sample mean in this range, if we go through the hypothesis test, we'll end up rejecting what we assume to be true, even if after the fact we find out it was in fact the true mean. So I had a little kind of thought experiment that we could do here, right? So I had some tuition data. I don't remember what year it was for. I guess it doesn't really matter. But it was a bunch of different schools. So I've got kind of their IDs. I think I stripped the names. Oh, I guess you've got some of the name. I left the city name, but maybe, no. Oh, I guess we have the institution names here. So anyways, we've got the tuition amount for all these colleges. It's population data. I grabbed it from every university from I think it was iPad's data source. So I can find the true mean salary, true mean tuition, right? By simply taking the average of that variable. That'll be my population mean. Here's my population size. I could count the number. Here's my true population variance, okay? I then took 1,000 samples, all of size 50. So I showed you another example like this where I generate some random numbers and then I take all these random samples. So here's my kind of random numbers that allow me to take 1,000 different samples of size 50, okay? So once I have those 1,000 samples, for each sample, I can find my sample mean, right? So here's my first sample. I just take the average, that gives me my sample mean, right? I could calculate my test statistic. Now what I did here was my test statistic will be the sample mean. Now if I had assumed that the true mean was in fact the exact true mean, right? So this was the scenario I was doing up on the board. The value we assumed ended up being the exact true mean. Here I kind of could cheat because I actually had the population data, right? So I'll subtract that assumed true mean, which ends up being the true mean, from my sample mean, divide by the square root of this known population variance divided by my sample size, which here, I could have probably put this in a cell, but I just use that count function to count up the sample. Each sample will be of size 50, so that shouldn't change, right? So I could get my test statistic. I could then get my p-value, and if I did a two-tailed test, all right, I would simply use that norm.s.dist, select my test statistic, which is in the cell that's getting kind of blanked out right here, comma 1, it would tell me the area to the left. If I wanted to do, I took the absolute value here of my test statistic. So the problem is if I do the area to the left and right, for every sample, that would have to be different. But if I just take the absolute value, since it's a symmetric distribution, it's always going to give me just kind of the area in one of those tails. That's kind of the area that's more extreme. I then multiply it by 2 to get my total p-value for a two-tailed test. Right? So I did this for every single one of these 1,000 samples. And I then use that if statement and say, okay, if that p-value is less than, I chose an alpha of 0.1, then put a 1, if not, put a 0. So 1 would mean that I'm rejecting, 0 means I'm not rejecting. Right? I then added up all those rejection decisions. So this should represent the number of times I rejected. Right? So I'm rejecting 90 out of 1,000 times, 92 out of 1,000, 107 out of 1,000. Well, notice if this is the number of rejection decisions, if I divide that by 1,000, that was the total number of samples I had. The percent of the time that I'm rejecting, or the probability that I'm rejecting, even though I shouldn't have been, because here I assumed the mean was in fact the true population mean. Notice the kind of probability that I reject when I shouldn't have been, it floats right around that alpha of 0.1, right? So it gets a little bit lower sometimes, a little bit higher sometimes. Now, if I wanted to get this true to be exactly 0.1, I need an infinite number of samples, which 1,000 is a pretty good approximation, but even there, it kind of dances around that 0.1 value. But this is kind of a nice example to see, like, if we had the population data, we could take all these samples and realize that, yeah, for 1,000, all these 1,000 samples, 110 times, we're going to make the wrong decision, right? And that's because wherever we set alpha, right, I can actually show you. Let's say I set alpha to be 0.01. Now notice I'm only making kind of type 1 errors about with a probability of 0.01 or 1% of the time. Right? So I don't know, this is kind of a nice little data kind of exercise to kind of prove that what we're doing with hypothesis testing would in fact work if we could observe what the true population mean was, which we could here because we had the actual population data, okay? All right. Also, I'm not expecting you to ever kind of create something like this, but I do think it is like a good thought experiment, kind of prove yourself with data as opposed to having to walk through and read through all the mathematical proofs. Okay? So we'll finish up on Friday, do some proportion to population stuff. Monday, we'll do some to population stuff where we only have sample variances. All right. We will then do some review next Wednesday and Friday. And based off the responses, I think the final is going to be open Friday through kind of Sunday. So you'll have kind of the weekend as well as Friday to do it. All right. So we'll do a review session Friday as well. Okay. And I realized the practice exams didn't upload right. So I'll get those uploaded when I'm done teaching my next class today. So if you want to start working through those, you'll have 2 practice exams leading up into that second exam. Okay. All right. I'll see you guys on Friday.